I will talk about insights from a pseudospectral study of a potentially singular solution of the three-dimensional axisymmetric incompressible Euler equation. And I will also dwell a little bit on Tygers and thermalisation. First of all, I'll explain this long title. But before I do that, acknowledgements. These are the two young people who did all the hard work. Sai Shweta is in the audience. Puneet started this as an undergraduate, but then he went to Germany to do a PhD. So most of what I'm talking about has been done by Shweta. We've had several discussions with several distinguished colleagues whose names I give here. And we have had generous support from all these funding agencies, including the National Supercomputing Mission and our supercomputing facility at the Indian Institute of Science. Here's an outline of my talk. I will begin with some history and motivation. Then I will tell you a little bit about models, the methods we use to study them, and then various results having to do with this criterion for detecting singularities, and some objects called Tygers, which were named Tygers by Uriel, Shomridhi, Takeshi, and Sergei Nazarenko, and thermalization, and another way of analyzing singularities called the Analyticity-strip method, and also some recent results on time analyticity, and then conclusions. So about 268 years ago, Euler wrote down the equations for an inviscid, incompressible three-dimensional fluid. Here's the celebrated paper, and it was written in French. If you want an English translation, Uriel produced a very nice one 15 years ago. So even though this equation, excuse me, some problem. Oops, no. There was some phase lag. Oh, excuse me. Right, even though this equation has been around for quite a while, what is known with certainty is that solutions of the two-dimensional incompressible Euler equation with analytic initial data do not exhibit a finite time singularity. But it is not known to this day if any solutions of the three-dimensional incompressible Euler, or also its viscous descendant, the three-dimensional Navier-Stokes equations, develop a singularity in a finite time if we start with analytic initial data. The answer to this grand challenge finite time singularity problem also has important implications for turbulence in fluids, even if we use the three-dimensional Euler partial differential equation, as was first conjectured by Onzaga and now has been proved. And some of this was already covered in earlier talks during this week. And if you want an overview of those problems, you can look at this paper by Greg Eying. Now, explorations of finite time singularity problems often use direct numerical simulations. Unfortunately, for the three-dimensional Euler or the three-dimensional Navier-Stokes case, these investigations, these numerical investigations have not yielded unambiguous results for or against a finite time singularity. And the situation up to about 2007 was summarized in this paper by John Gibbon. And you know, very distinguished scientists have worked in this area, and that just tells you that it's a very hard problem. And they've tried many, many things. So in this talk, I will not attempt either to look at the three-dimensional Euler or the three-dimensional Navier-Stokes PDE, but I will look at the three-dimensional axisymmetric Euler equation and investigate a potentially singular solution of this equation. And why do I want to do that? Because in an important paper by Luo and Howe, this equation was studied by a numerical method which is called the hybrid Galerkin and finite difference method. And this is the title of their paper, Potentially Singular Solutions of the Three-Dimensional Axisymmetric Euler Equations. So this brings me to the motivation of this talk. Given the importance of this problem, in fact, Uriel would keep on bugging me about this. He said, look, how do we know they're right? I mean, so it is important to study this potentially singular solution by completely different numerical schemes and another singularity detection criterion. By what do I mean by another? They use the one which is based on this celebrated theorem by Beal, Kato, and Maida, which is remarks on the breakdown of smooth solutions. I will tell you what this criterion is as we go along. And so not only did we use a different scheme, we developed a Fourier-Chebyshev scheme for this problem, a pseudospectral scheme. And we used a completely different singularity detection criterion, which was first developed in this very important paper by Sulem, and Frisch. You must have seen Professor Ellen Frisch at lunch, who's been attending the lunch things at least. And they came up with a very nice method, which is called the Analyticity-strip method, which looks at possible singularities and requires a pseudospectral simulation. Okay? So we looked at a Fourier-Chebyshev pseudospectral simulation for reasons that will become clear as I go along. All right, then coupled with this, there is also the issue of thermalization. You heard in the previous talk by Mark that whenever you have a Galerkin truncated pseudospectral study of such hydrodynamical equations, you get thermalized solutions. The history of such thermalized solutions goes back at least to 1950, this paper by Hopf on the Burgers equation, and by T.D. Lee on the Euler equation. And this you have learned already in Mark's talk, that in the 3D Euler case, thermalization would show up as an energy spectrum where the energy goes as k squared and not as k to the minus 5/3 as in the celebrated Kolmogorov phenomenology. So this was a mystery. Everybody worried about it until this very nice and important paper from the group of Marc Brachet, who you just heard the previous talk. And this is a pseudospectral numerical study of the three-dimensional Euler equation, spectrally truncated. And you can see in the tail here that the k-squared spectrum is developing. So that is the spectrum that T.D. Lee had foreseen. And of course, it also provides an artificial viscosity for the low K modes where you do see a Kolmogorov-like spectrum. But that's not the point of the talk today. So I just want to show you that 3D Euler, spectrally truncated, will lead to such thermalization. So if we are going to study singularities or potential singularities by pseudospectral methods, we must make sure that we can take care of such thermalization effects. All right, so now down to the hard work. The 3D incompressible Euler equations are given here, standard notations. Omega is the vorticity, U is the velocity field. Psi is a vector-valued stream function, which is related to the vorticity by this Poisson equation. Now we're going to look at the axisymmetric case. So please don't look at all the details, but here is the velocity in cylindrical coordinates. These are the unit vectors. And it is advantageous to introduce these variables, u1, which is u theta divided by r, omega 1, omega theta divided by r, psi 1, psi theta divided by r, where these are the angular components. And if you put that in the original Euler equations, this is the set of equations you get, where u stupor r is minus r psi z stupor 1, u, etc. Okay? And these are the standard derivatives. Okay. Now, all these variables are well defined. If you're very mathematically inclined, all the conditions are given there. So these are well defined so long as the solutions to this are that level of smoothness. And because we have introduced variables, which there is an origin now because of cylindrical coordinates r equal to 0 is special, we also have to take care of that. The boundary conditions that we use an L periodic boundary in the z direction, and a no flow condition at r equal to 1. So it's still axisymmetric. And the pole condition at r equal to 0. So these are the conditions. And now we use the initial data suggested by Luo and Howe. Okay? It looks messy, but doesn't matter. This is the initial condition that we will look at with all the boundary conditions. All right, so they use some Galerkin and finite difference. Our strategy was to use a completely different method. So if you study elementary mathematical physics, if you have to do something in cylindrical coordinates, this is a particularly convenient representation. So any function of r and z, it's axisymmetric, so I don't have to worry about theta, can be expanded in this Fourier-Chebyshev series. These are the expansion coefficients. It's periodic in z, so it's the conventional e to the I k z. And then these are the Chebyshev polynomials of the first kind of order n. So if you look at your simulation domain, this is what it looks like. I've put some vorticity field on it. But what I want you to note is that with this basis, the collocation points cluster near the boundary r equal to 1 and also near the origin, okay? So that's the grid which is generated for us by this representation. So all the results that I'm going to talk about, or at least most of them, are contained in this paper, which we published recently. And let me, before I get into details, tell you a little bit about the qualitative nature of this flow, which is taken from this paper. This particular diagram is taken from this paper. So this is the cylindrical domain. You have u dot n equal to 0 on this at r equal to 1. It's periodic in z, and the initial velocity is such that the u goes this way and u goes this way. And then if you look at there's a secondary flow which is set up, which looks like this. And so at z equal to 0 and r equal to 1, there is a stagnation point. And this has been known in the mathematical literature for a long time that there is a possible finite time singularity here. So that's the point that we will look at carefully. These are the two conserved quantities, the energy and the helicity, which I have written out in terms of these components. And now let me tell you which is this celebrated criterion of Biel-Kato and Maida. When you look at Euler, you might say, oh, do I have to look at every derivative? It might blow up in so many different ways. And what Biel-Kato and Maida taught us was that you just need to look at the L infinity norm of the vorticity, and you integrate it from 0 to time capital T. And so long as this integral is less than infinity, then you don't have a singularity. But if there comes a time capital T at which it diverges, well, that is the time at which you have the singularity. All right. Now, a little side issue, which I will just talk about briefly, that I will also look at a simpler one-dimensional model, which I will call the one-dimensional Hilbert transform model, which was also studied in this reference that I told you about, and by Luo and Howe, which is this set of equations, duz, this thing, that thing, and that's the Hilbert transform, which for this 1D problem is the analog of the Biot-Savart law, which you heard about in Professor Migdal's talk in the morning. And these are the initial data that we will use. I still have not defined U, etc., which is here on the next slide. U is U1 squared, omega is omega 1, and Vz is dr of psi1z. We will see that the singularity will develop at r equal to 1, and we are going to look along the z direction. So when you look at those plots, you will see that this is a natural sort of model that you want to write down. And in this model, you can actually prove that there is a finite time singularity. But all that we say about the 3D Euler axisymmetric case, we will also test on this 1D Hilbert transform model. All right, now for Tygers. Now, pseudospectral investigations of potentially singular solutions have shown localized oscillatory structures, which these 4 authors call Tygers, at points of positive strain in the velocity field. I'll tell you what that means in a minute. They were first introduced in the context of the one-dimensional Burgers equation, and also the two-dimensional Euler equations en route to thermalization in spectrally truncated pseudospectral DNSs. And note that in the Burgers case, we do have a finite time singularity, whereas in the 2D Euler case, we don't. So Tygers by themselves do not signal a singularity. Okay, so here's the first paper, which talked about these resonant phenomena, which they call Tygers. And at least 2 of the authors are probably here. And you see this, this is an oscillatory structure. If I blow it up, you'll see there are significant oscillations there. They're far away from the shock in the Burgers equation, all right? This is the resonant point. And we will see the similar structures in the solution that we talk about. Now, a note on the analyticity-strip method, which is the following, that if you do carry out a direct numerical simulation in a periodic domain, then to figure out whether or not you have a singularity, it is useful to complexify the spaced variables. And then there is an analyticity strip of width delta t. And if you look at the Fourier transforms of the velocity field, let us say, you forget about the power law prefactor, but it decays exponentially e to the minus k times delta. And this delta is the width of the analyticity strip. So by looking at suitable spectra, I can measure delta. And then we can estimate if delta t goes to 0 at a finite time t star. So if you're thinking in complex space, this is the singularities come in from complex space and hit the real axis at that time. Now, we had to generalize this to study the Fourier-Chebyshev case, because this is for conventional Fourier. And suffice it to say that it can be done, and it is described in our paper. So I won't go through all the details of that. All right. You have to worry about errors. I mean, this is, if I were giving a physics type talk, I wouldn't dwell too much on it. But if you are looking at singularities, you better be sure that you are doing things very, very well, which Sai Shweta has done. There was a Poisson equation, which was there on one of my early slides. She has investigated 2 different ways of solving the Poisson equation, compared their relative errors. And you can see that both the ways of solving the Poisson equation that she has used are very good. And she has used sample functions to test that both these solvers are very good. And then we have used it in our Fourier-Chebyshev scheme. Another important way of validating your code is to compare it against exact solutions that exist. And luckily, there were such exact solutions. I give you the reference. It's from a group of Bérengère Dubreuil. And this is a steady state solution for the given boundary conditions. All right. And so when we write our Fourier-Chebyshev code, we check that we can reproduce these stationary solutions. Okay, so this is a plot to show you that we were doing a pretty good job on these stationary solutions. The next thing to check, of course, is whether all quantities that should be conserved are being conserved very well. And Mahendra told you about his 2D Euler studies, how they had to use a special solver to get good data. So here also, we have worked very hard. And you can see that the energy, this is the percentage error. So up until this time, it's doing pretty well because it's 10 to the minus 8%. The helicity was 0, so it stays pretty much 0. And this is the plot of the Beal-Kato-Maida type. So log of omega infinity, and it rises slowly, and then it seems to become very large. This black dashed line here is the time of potential singularity contained in the work of Luo and Howe. So to this extent, of course, our results are in agreement with theirs. I have marked two other lines here, one in red, the other in blue. One says Tygers born in U1, and another says Tygers born in omega 1. So you can see that these oscillatory structures that I talked about do come up here, and I'll show you more about them as we go along. Now, I said that to use the analyticity-strip method, you must look at certain spectra. If it's just standard pseudospectral, you can just use the energy spectrum. But here it was convenient for us to look at the Fourier transform over Z only, then it is a function of K. This is a fixed R, or we fix Z, and then we take a Chebyshev transform over R, and we get M. So these are spectra that are completely well-defined. And now I show you a plot of some of these spectra. So this is the first spectrum I talked about, and we're going to look at R equal to 1, because that is where the singularity occurs. And this is a semi-log plot versus K. So you see initially there is an exponential decay, and the rate of that decay will at least will give us the width of the analyticity strip, which I'll show you later. And then you see it becomes slower and slower. And what you cannot see is that there are very high frequency oscillations here. There are even odd oscillations, which have to do with the symmetry of our initial condition. And eventually it completely straightens out. So this is thermalization. Similarly, I can look at in the Chebyshev direction at Z equal to 0. And here also initially an exponential decay, and then it goes up. And that's again thermalization. So we can compare thermalization in various different models. So here is thermalization in conventional one-dimensional burgers. Mark mentioned the K to the 0 spectrum that's there, and this is how it behaves as a function of time. So it's more or less thermalized. 1D Hilbert did not do very well. And of course, it's a slightly peculiar problem because only the L1 norm of the velocity is preserved. So, okay. And the 3D axisymmetric Euler is more or less thermalizing. At a practical level, in a model where you see a finite time singularity, you have to be careful because, even thermalization, there are numerical issues that arise. So how well you thermalize depends on how much it's just blowing up. So this shows you a little bit about, let me just show you one of the, how the energy gets transferred down in K-space, okay. So here's the movie, there's the energy growing, and you can see various, the U1 and the omega-1 and the spectrum, all right? So that's how it slowly thermalizes. By the time the Tygers are born, really, you are not solving the partial differential equation in question. You are solving the Galerkin truncated system, which is like if you're a statistical mechanician, you will say that's the microcanonical evolution of that truncated system. But here are the Tygers. So this is U1 as a function of Z. All this is at R equal to 1. And you see the sort of oscillatory structures that I showed you for the Burger's case. They're showing up here. And if you zoom in here, you see these high frequency oscillations. And similarly, you can look at omega-1 as a function of Z, also at R equal to 1. And here you see the oscillatory structures again. You see them earlier in omega-1, not surprisingly, one higher derivative than you do in U1. And, visually or by any means, you can, find out the time at which these structures are born, and you can plot them versus the Galerkin truncation wavelength, or 2 pi over kg, and that's how they behave. So you can examine the time of birth of these Tygers. Now, does the same thing happen in the 1D Hilbert transform model? The answer is yes, of course. That's why we studied this model also. And of course, here you can study it with much better resolution than you can in the 3D Axisymmetric Euler case. Again, you see as a function of Z. Now we have only Z, this variable U, and you see these oscillatory structures, which are the Tygers. And here you also see the width of the analyticity strip going down. And here is the omega variable, again, the Tygers. And here you see the beginnings of thermalization, though it doesn't go all the way because eventually the solution blows up. You can look at more complicated pictures. For example, these are space-time plots, Z here, time here. This is for the Burger's case. This has been studied by Marc Brachet and his co-workers, Pablo Menini also, for the Burger's case. You get these very nice sharp lines once this structure develops. But these lines, you see, the Burger's is a wonderful model. We know just about everything about it, and everything is nice and simple. The moment you go away from it, these sort of boundaries don't look so great in these other models, like the 1D Hilbert transform model or the 3D-dimensional axisymmetric Euler. So you can think of these as the Tiger propagation fronts, and you can fit them to various forms of the function of time. So this is the paper I was referring to. They looked at the dynamics of these partially thermalized solutions of the Burger's equation. The analogous plots for these two models that I'm talking about, the 1D Hilbert transform model and the 3D axisymmetric Euler, we have, but they don't look as clean as in the Burger's case. All right, so of course, the grand goal from the point of view of partial differential equations is to say, do you or do you not have a singularity? And we can fit by looking at the spectra that I told you. We can find the log decrements of these spectra. From those, you can plot the width of the analyticity strip. Here I do it for the even part of the oscillations. And as a function of R and T, and it is fastest fall is at R equal to 1, which is the wall, and this one falls fastest at Z equal to 0. So from such plots, we can extract, let's see, when this width is going to 0, right? And over here, again, we have marked where the Tygers first appear in omega 1. And if you're sufficiently careful, you'll keep track of the even and the odd ones separately. And then you can fit over here, and it seems to be going to 0 as a power law. And you can ask that, well, in this fit, you can do the fit in 2 ways. One is for T star, you put in the Luo-Howe estimate, and then you see whether your data are consistent with the Luo-Howe estimate. And the answer is yes, they are consistent with the Luo-Howe estimate. Or you can do it another way. You actually treat T star as a fitting parameter. And then you ask how well are you doing for the singularity. And well, you can get a number. I think the number we got by doing the analysis this way, I'm showing it for the width of the analyticity-strip, which we get by doing the Chebyshev one, and there is a fit. And this is the result we get. We have, fewer decimal places than Luo and Howe do because they have an adaptive grid. So they can, of course, go much closer to the singularity than we can. Our main advantage is that we can use a completely different method of analysis to see whether everything is consistent or not. So when you look at such plots, you should actually ask, is there a real slope or not? And if you're sufficiently careful, you will carry out a local slope analysis, which is this blue line, red line. And okay, that's how well we do. All right. And this is for the other case, that is in the Fourier, in the K direction. So this is delta even. Again, we can do a power law fit. And this time we are using the Luo-Howe number. Okay? And this is again consistent. So it's nice, at least in this field, we are all agreeing that there is a singularity, which was not the case in 3D Euler numerical studies. Many very, very distinguished groups and scientists disagreed. Some people said blow up yes, others said blow up no. And so here, at least in this case, we have agreement. And not only this calculation from our group, which has concentrated on the blow-up thing, I want to highlight 2 other recent studies. One is by Dwight Barclay, who also did it with a Fourier-Chebyshev scheme. I've talked to him, he said the point of view he took is, yes, the singularity is there. So it wasn't as if he was trying to show that the singularity is not there. But then he actually, this is a very nice physical paper, where it gives you a physical sort of understanding of why there should be a singularity. It is a peculiar thing. You see, when you have a singularity in burgers, you understand because it's compressible. This is incompressible, but something funny is happening near the boundary at r equal to 1 and at z equal to 0. Then there was another very nice paper by Hertel, Bess, and Frisch. This used a Cauchy-Lagrange method for the same problem. Now, Cauchy-Lagrange is too complicated to explain to you in a few minutes, but Uriel is there. You can catch hold of him over dinner tonight. He can tell you everything about it. The good thing about the Cauchy-Lagrange method, if I can just highlight one of its virtues, is that it is a semi-Lagrangian method. So it does not suffer from having to use a very small time step to maintain this CFL condition. Okay. Of course, the other thing is then you have to do a lot of interpolation to get your grid, your particles go off grid and so on. But they could do it. And so it's a very nice thing, which is for Tobias's PhD thesis, and it's been published in this journal. So, and all these papers agree that as far as we can check numerically by several different schemes, numerical and analysis of singularities, there seems to be a finite time singularity in this 3D axisymmetric Euler thing, which is at the boundary at r equal to 1 and near z equal to 0. Okay. Now, before I conclude, let me tell you about some very recent work which Shweta has been doing. It is again inspired by some work done by in the group of Uriel Frisch, by Cornelius Rampf, Uriel Frisch, and Olivier Hahn. And I really would have liked to give this talk after Cornelius's talk. And that is how it was in the original program, but so many speakers had so many different constraints because of time differences that I had to move my talk. So I will not tell you too much. I think Cornelius should tell you about the beautiful work they have done for early time resonances and singularities in the inviscid Burgers equation. So we've used this paper of theirs as a model, and we have explored these singularities, which are now complex time singularities, which lead to resonances which look like an eye, which is why they call them eye of the tiger. But these are just early time singularities. So I will try to explain to you what they mean. I will not tell you what Cornelius will tell you next week, but at least let me tell you a little bit about how to study these problems. So if you want to study the time analytic structure of PDEs of the sort that we have been talking about, and then we can expand all functions at some spatial coordinate r in some Taylor expansion. Okay, r could be a one-dimensional spatial coordinate in a 1D model, or it could be a three-dimensional spatial coordinate in a 3D model. And G tilde R vector n are the time Taylor coefficients of all the fields. Okay, we will abbreviate this to make it G sub n, and we will not restate the implicit dependence of the time Taylor coefficients on R, excuse me. All right, so here are the models that we have got accustomed to by now. So we first do the one-dimensional model, which is obviously easier. It's the 1D Hilbert model, but even this model is considerably more difficult than the 1D Burgers model. Okay, so how do we proceed? We had the equations, which I will not repeat for you. We substitute this Taylor representation into those equations, and we compare the coefficients of powers of t to the n, and that leads us to recursive relations between these Taylor coefficients. So for the omegas, the omega n's, for the u's, the u sub n's, and the v sub n, and that's the Hilbert transform. All right? So in the Burgers case, it's quite easy. You substitute it back in the equation, and you can actually work out these things order by order. And they had up to 70 time Taylor coefficients, which we also did. And this Shweta did. For this 1D Hilbert model, you can do all the symbolic stuff and do it actually analytically using Mathematica. And if you plot u versus z, then you see these oscillatory structures. Okay, this is with only 0 terms, and then you have 20 terms, and then you have 76 terms. And these oscillatory structures are reminiscent of Tygers, which we just talked about. In their paper, Rampf, Frisch, and Hahn called them early time Tygers. There is a sort of implicit and Galerkin truncation here, because when you keep a finite number of Fourier modes. Suppose you start with a single mode initial condition like sine of x. Then when you generate the next order term, you get up to sine 3x, next order up to sine 5x, and so on. So, you know, so there is a sort of Galerkin truncation, and these oscillations are sort of like Tygers, but not directly the same. They occur at much earlier times, okay? And they are related to singularities in the complex time plane. So some of us, like Jointo and I, started life in critical phenomena, where people looked at such series and, you know, tried to find where the singularity is. Of course, there we were always interested in the real Z singularity, but often singularities occur in the complex plane. That's why we had to do Pade and so on. So here also people do such things. And it turns out that you have to find the radius of convergence of these series. And it is advantageous to make what are called Mercer-Roberts plots. So, you know, this is not something you dream up overnight, but it's well known by now. You define these BKs and cosine theta Ks, which are these combinations of the UKs, which were the time-Taylor coefficients. All right. And if you write it out and you look in the limit k going to infinity, then the dominant term is 1 over r, where r is the radius of convergence of the series. So by making plots of bk versus 1 over k and extrapolating to k equal to infinity, you can find out the radius of convergence of the series. And of course, the radius of convergence of the series depends on where you are, okay? And so it depends on, this is the 2 pi periodic domain, and you see this thing. All right, so you can plot, make polar plots, and the singularities reside on these types of things, which is why Rampf and Frisch and Hahn call them eye of the tiger. Okay, so I'm not describing every detail because I'm sure Cornelius will describe these to you. And okay, all right, harder problem. Can we do this for 3D axisymmetric Euler? Because I can't, but certainly Sai Shweta can, and I will tell you roughly how it is done. It's much worse because you have to do time-Taylor expansions of U1, omega 1, etc. And when you put these time-Taylor things back into the 3D axisymmetric Euler equations, you get these recursive relations. So if you have the initial data, you can just feed it in and solve. Okay. Now, there is one important difference, that in this case, we have to solve a Poisson equation. Once we have omega 1, we still need psi n1, and to get the other coefficients, we need to solve this Poisson equation. And we could not find a very convenient way of doing that with Mathematica. So what Sai Shweta did instead was to solve the Poisson equation. Oh, excuse me. By numerically, okay? So in space, you put down a grid, and you again use a Fourier-Chebyshev grid, and you solve it, and then you get the coefficients. But you know, this is a delicate matter in the following sense. She did the calculation with double precision first, not very good. And then my only contribution was to say, well, try quadruple precision, which she did. And then everything fell in place. Okay, so precision matters. And to make a long story short, I will just say that she has the same types of plots. The radii of convergence is a function of the position along the z direction. So this is at r equal to 1, little r equal to 1. And again, this eye-like structure of the singularities in the complex time plane. Okay? And these are early time. So these are not related to the Tygers that I talked about earlier. This is early time asymptotics, and Ram, Frisch, and Hahn have called these early time Tygers. And they have also talked about methods for, okay, we can do it, and these models, which are far more complicated than the 1D burgers, about which we know many, many things, do show this stuff. So in summary, we have developed a Fourier-Chebyshev pseudospectral DNS to examine this potentially singular solution of the radially bounded three-dimensional axisymmetric Euler equations. I hope all of you understand all the words in that long title by now. We have also studied this 1D PDE, which has been used to model this potential singularity along just the one direction at r equal to 1. And we have demonstrated that these singularities are preceded in any spectrally truncated DNS by the formation of Tygers. But you shouldn't get daunted by that, because you can use the analyticity-strip method to obtain a reliable estimate for the potential singularity time. So now there is good numerical evidence from different types of calculations for a potentially singular solution of this radially bounded three-dimensional axisymmetric Euler equation. And now, of course, we need a real proof, and this is being examined by mathematicians. There's also a preprint out by Howe, but okay, I cannot tell whether it's really proved or not. And this axisymmetric Euler equation and the 1D model above provide good testing grounds for studies of Tygers and thermalization, which you might also be interested in from the point of view of statistical mechanics. And then in our most recent work, we have also explored the time analyticity of solutions of this 1D and 3D model in the way that Ram, Frisch, and Hahn have done. And so I thank you for your attention, and I'll be happy to answer questions while you watch this video one more time. Thank you.
Questions?
Yeah.
Sure.
One sec.
Oh,
One sec.
okay.
Any other questions?
Yeah.
So Rahul,
Yes.
good talk.
Thank
so
you.
For the burgers, we get this analyticity strip singularity there as well. I mean, where is it? Where is the singularity for burgers equation? For,
Exactly at T star. I mean, this was the earliest work. This is Sulem, and Frisch from what, 1980s?
No, but the position, where is in the X space, where is the singularity? Like here, the cylinder, you are finding it in the middle of the cylinder, but in burgers, where
that is exactly, yeah, it's the position of the shock depends on the structure.
Is it at the shock? The
initial, yeah, no, excuse me. I'm getting confused by two things. One is the time of the singularity. The other is the spatial position of the singularity.
Yeah, spatial.
So the analyticity strip method gives you the time.
Okay.
And of course, you can.
But the complex strip gives you where does it?
Yeah, it gives you the time. You can get the time. And you can do for different initial data. Because as you know, I mean, for the Burgers case, you can actually predict the time analytically, and then you can, calibrate against that.
Can somebody check whether there is some question from the Zoom participants?
Sasha has
yes, I'll give Sasha, but unfortunately, I'm not on Zoom. So let me see. Yeah, there is.
Beranger has a question.
Beranger, you'll be next. I'll give one question, then you ask.
I'm talking about is just angular velocity going like 1/r. Does your axial solution in some situations become this singular vortex?
No, I mean, it is what it is. I mean, I showed you the plot of various u's and omegas along the z direction, and their change becomes sharper and sharper. And again, in the 3D Euler case, it's not a singular solution in the sense that nobody can prove that there is a finite time singularity starting with some data. Many people have tried.
It is a stationary solution. What I'm talking about.
Yeah, so the stationary solutions I mentioned, which was from the group of Dubrul, they are there, but they are not singular. They stay stationary in time. Okay? For this axisymmetric case also, which we use.
Your question, please.
Yes, hello Rahul. Thank you for this very nice talk. My question is exactly related to this paper, the Le Provost et al. Paper. So in this paper, we give the shape of we give shape of stationary solution, and we show that they obey simple relation of the type R times V azimuthal is a function of the stream function, and vorticity azimuthal divided by R is also a function of the stream function plus a contribution from the azimuthal velocity. These are stationary solutions, but these are also equilibrium solutions because this is statistical mechanics. And my question, and this solution were true only if there were no singularity in some sense. But my question was that did you check that your solution satisfy this relation or not? Because you are doing Galerkin truncated, you are at equilibrium in some sense. So my question was that do you observe this or not?
Yes, I think that was the first thing that Sai Shweta checked. That for these stationary solutions from your group, the energy remained constant for very long until eventually there was some numerical thing which, right? Probably Sai Shweta can answer. You have the mic. Yes. Oh, no? All right. We'll give you another mic.
Is it now audible?
Yes. Yes. Yeah.
So can you once repeat the question?
Question is, these are equilibrium solutions. So first of all, did we check equilibration with them? But I think you checked first of all that they were time independent.
So they were
very large time. Okay, continue.
So they were stationary for as long as I could evolve it, unless roundup errors were building up.
Okay, my question was regarding your solution, the Liu solution. Did you check whether angular momentum was a function of the stream function, for example, or not?
No, it wasn't. So this is not.
Yeah, continue. Please answer.
So because this is also not stationary, I don't think it will follow the same relations that your solutions followed.
And even at the time of the Tygers, it does not follow?
No.
After you have thermalized, it does not follow?
So I will check again and get back to you, but I do not think they have a relation with the stream function.
Okay, thank you.
All right.
Okay, my questions, and I don't know, for discussion, I throw questions also. It can be viewed as comment or questions. First question is, are there any experiments which can prove this?
No.
Okay, obviously, because you're considering an ideal case. And see, in my view, when even if it is an incompressible flow, when you have two vortices rotating in a box, opposite direction, that actually produces, any instability is produced by oscillation, locally or at various places, randomly or in a particular manner. It depends on how where the instability is introduced, how it is introduced, the rate at which it is introduced, and at how many places it is introduced.
The first part of your question.
Yeah, I'm not completed.
But still, so the motivation for this study really comes from applied mathematics, not from an experiment. In fact, I think mathematicians have proved that in this particular case, if you introduce even an infinitesimal amount of viscosity, this singularity goes away. Yeah. So that's point number one. Point number two is you seem to say that, just putting a little bit of vorticity will lead to such things in Euler. that if it were so simple, you know, there are a lot of people who have spent decades trying to look for a finite time singularity in the 3D Euler with all sorts of, you know, imaginative initial data like anti-parallel vortices, parallel vortices. And in a strict sense, they have not been able to produce a good candidate for a finite time singularity. So, you know, we have to rise above the qualitative level and actually get down to hard calculation.
No, I'm not telling that it will finally equilibrate or it will have finite time singularity or all those. It depends on the initial condition, the boundary condition, and also it's random. You cannot predict because there are pressure fluctuations. See, when you introduce a singularity in incompressible flow, there are pressure waves and pressure fluctuations.
You're right. So you were saying many things in one sentence. All I'm saying is all those effects are there. It is true that everything depends on initial conditions, but this is the best we can do for a finite time singularity in 3D axisymmetric Euler. The problem is still mathematically, even numerically open in 3D Euler and 3D Navier-Stokes. So, you know, anybody should try it. And there is a Clay Math Prize for $1 million if you can prove it for the 3D Navier-Stokes.
You mean 3D Navier-Stokes, what needs to be proved?
Okay, I'll give you a correct statement
in
the discussion session.
Whether there is a finite time singularity for a 3D Navier-Stokes equation with smooth initial condition, say in compact manifold, say on a torus.
No, if it is Navier-Stokes,
well, that's a problem. If you know how to solve it, you get 1 million. If you don't, then you don't. But let me stop here this discussion, and people can continue after privately. And I remind you about the dinner, and you have 2 hours before the dinner, so just use it wisely. Thank you.
Thank you.
Let's thank Rahul again. Yes, yes.